The purpose of this video is to review how to solve logarithmic equations. I'll be using different techniques. However, some of the examples could be solved using other methods. Okay, so just remember that sometimes there are different ways of solving the same equation. First, let's review the log f of x equals the log base b of x. Let's assume that b has to be greater than 0 and b cannot be 1. However, I'm going to restrict b to be greater than 1. It will be the graph will look like this. Notice that this graph experiences a vertical asymptote at x equals 0. Its domain is from 0 to infinity. In other words, all positive numbers. The range goes from negative infinity to infinity. In other words, all real numbers. So domain not positive, the range all real. It's imperative that we remember that the domain is all positive numbers. Every time we solve an equation, we must check the answer because the log can only take as a domain, as an input, positive numbers due to the domain. So let's go over several examples. Example number 1, log base 4 of x equals 2. I'm going to solve this one based on the definition of logs and the relationship between log and exponential. This means that 4 raised to the 2 equals x. So every time I have a logarithmic equation, of course, one way is to solve that, to change to its equivalent exponential equations. In this case, 4 to the 2 equals x. So 4 squared equals x. Therefore, x equals 16, and we are done. Of course, if logging 16 in the original equation, we can find the log of 16. Let's try example number 2 using the same technique. If I have log of x plus 6 equals 1. Okay, every time we deal with logarithmic, we always have a base. In this case, we are dealing with the common log function because it's base 10. There is no number, but that will be your default. The base will be 10. So once again, 10 raised to the 1 equals x plus 6. The base 10, which is here, raised to the 1 equals this argument. Of course, we know that 10 to the 1 is simply 10 equals x plus 6. Isolating the x, we may subtract 6. So therefore, x equals 4, and we are done. Example number 3, using the same technique, it would be log base 3 of 3x minus 1 equals 2. Same old, 3 raised to the 2 equals 3x plus 1, 3x minus 1. 3x minus 1, of course, 3 to the 2 will be 9. We add 1. So 3x equals 10, we divide by 3, therefore x equals 10 thirds. Example number 4, using the same strategy, would be ln of x equals 3. In this case, we know on example number 2, we're dealing with the common log where the base was 10. Every time we see ln, of course, we know this is the natural log. So the base will be e, which we don't obviously write. So ln, the base will be e. So therefore, e to the 3 equals x. And this one, we can find the calculator. If we want to approximate it, how much will be e to the 3? 20 point approximately, so x is approximately 20.08. 55. We are done. Let's try some other examples. For the following set of examples, we're going to use 2 rules that we already reviewed. One is the following. If log base a of m equal log base a of n, as long as it's the same base, of course, the arguments must be the same. Also, we can use the power rule. The power rule states that r times log base a of m equals log base A of n raised to the r. If the log is being multiplied by a constant, this number can be brought inside as the exponent. So let's go over a couple of examples and remember to always verify the work. What if we have the following? Example number 5. Log base 4 of x plus 2 equals log base 4 of 8. Notice that we have log base 4 of something equal log base 4 of something. What can we conclude? That the two arguments must be the same. Therefore, x plus 2 must be equals to 8. Therefore, x equals to 10, and we are done. Example number 6 would be an extension on number 5. If I have 2 times log base 5 of x equals 3 times log base 5 of 4. Notice, of course, that we can bring that exponent using the power rule. These 2 times, these 2 can be brought as exponent. Likewise, this 3 can be brought here as exponent. So what do I have? As per the power rule, we may conclude for log base 5 of x equals of x squared equals log base 5 of 4 to the 3. Using the equality, this one is called the equality rule and the power rule. Using the equality rule, we may conclude that x squared equals 4 to the 3, that would be 64. And how do I solve for x? We can take the square roots of x equals plus or minus 8. So plus or minus 8. In other words, x equals to -8 or x equals to 8. Notice that we have 2 solutions. So we need to go back to the original problem. Of course, when x equals -8, we may not find log base 5 of -8. So therefore, we eliminate this one. So we end up with only one solution, x equals 8. Let's go over to other examples. We'll use the same properties as before. Once again, I'm multiplying 1/2 times this equals 2 times log of log base 3, log base 3. This 1/2 can be brought here as exponent. These 2 can be brought here as exponent. Therefore, we have log base 3 of x to the 1/2 equals log base 3 of 2. Same log base, therefore the argument must be the same. So therefore, x to the 1/2 must be equals to 2. But x to the 1/2 is the same thing as the square root of x equals 2. How do I solve for x? We can square. So therefore, x equals 4. Notice that when I punch in 4 in the original equation, we'll be finding the log base 3 of 4. So we have not broken any rule. Just to recall, what is the rule? The arguments must be always greater than 0. After all, that is your domain. Let's go ahead and try example number 8. Very straightforward example. Log base 10 of equals log base 10 of. Same base in the log, the arguments must be the same. So therefore, 4x minus 20 equals 4 minus 2x. Isolating the x, of course, we may add 2. So I have 4 plus 2, that would be 6x equals -20. We may add it here. So 20 plus 4, that would be 24. If we were to divide by 6, of course, x equals 24 over 6, which would be 4. Yeah, here we got 4, so the same number. However, be careful when we plug in the number, we cannot violate the rule, the domain. So when x equals 4, 4 times 4 is 16 minus 20, that would be -4. That sounds awful. Actually, same here. When x equals 4, 4 minus 2 times 4 is 8, that would be -4. So this is a big no-no. Why? Because the log cannot take negative numbers. So this one will have no solution. But the number that we believe was a solution, it does not work because the domain of the log must be all positive numbers. Two more examples. I chose these two for particular reason that we can have several methods to solve the same problem. However, notice that once again, these 3 times, I can bring these 3 as exponents. So let me work with this one as first, log base 2 of x minus 1 cubed. Now, we will learn in a few, or you already learned that what happens when we add logs of the same base, we do something, so we can multiply. However, we know how much is log base 2 of 4. What are we asking here? 2 raised to what number gives me 4? Of course, the answer would be 2. So if we don't see that this is equals to 2, then we can use other properties. However, we're just simply going to say 2 equals 5. We may subtract that 2. So we have log base 2 of x minus 1 cubed equals 5 minus 2, that's 3. And now we can just change to exponential. 2 raised to the base equals 2 raised to the exponent to the 3 equals x minus 1. So what do I have here? That x minus 1 cubed equals 2 to the 3. Okay. Here, of course, if you remember how to solve exponentials, we can take the cube root. The cube root both out of the equation. So I have what? X minus 1 equals 2. We add 1, so x equals 3, and we are done. Because when we plug in 3, 3 minus 1, positive number equals 3. Example number 10, same old. In this case, now we are subtracting. So of course, we know the quotient rule. However, first, let me clean this. 2 times, I can bring that as the exponent. So log base 3 of x plus 4 squared. Now, what are we asking here? 3 raised to what number equals 9? Of course, the answer is 2. 3 squared equals 9. So we can just, instead of using the quotient rule, we can just simply say minus 2 equals 2. We add 2 so before. Now what do we have? Base 3 raised to the 4 equals that. So x plus 4 squared equals 3 to the 4. Last time we checked 3 to the 4 is 3 times 3, 9, and so that would be 81 equals x plus 4 squared. We take the square root. So x plus 4 could be the square root of 89 plus or minus. So it would be negative 9. Be plus or minus 9. We may subtract 4. So x equals negative 4 plus or minus 9. So 2 potential solutions. What are my 2 solutions? 9 minus 4. So x equals 5, or negative 4 minus 9. X equals negative 14. We need to verify both numbers. Of course, when x equals 5, 5 plus 4 will be positive. So x equals 5 worse. When x equals negative 4, negative 14, sorry, plus 4, that will be negative 10. So if we plug in negative 14, we'll violate the rule, my domain rule, that will give me x log base 3 of negative 14 plus 4, that will be log base 3 of negative 10, which does not exist. For the next 2 examples, we are going to piggyback, or we're going to use the following rules. If you recall the product rule, when we are adding 2 logs of the same base, we could multiply the arguments. Thus, log base b of m plus log of b of n equal log base b of n times n. Likewise, the quotient rule tells us that when we are subtracting, when we have log base b of m minus log base b of n, we may divide the arguments. So that will be our 2 rules we are going to use for the next 2 examples, the product rule and the quotient rule. So let's go ahead and solve this too. So the first example, what do we have? We are at log base 10 plus log base 10, same base on the sum. We may multiply the arguments. Will be log of what? X times x plus 5 equals 1. Okay, I think this equals 1, not 2, equals 1. Now what do I have? Log of x squared plus 5x equals 1. Let's hold on this one. I think I wrote the problem incorrectly. Let's go ahead and continue with the other problem. Sorry, I stopped the video just for a second. It's a log base 10 of x plus log base 10 of x plus 15 equals 2. So it'll be 15 equals 2. So let's recap. When I'm adding with the product rule, we multiply the arguments. So it'll be x squared plus 15x equals 2, not 1, 2. So now what is my base? 10. So 10 squared equals x squared plus 15x. Always remember, there is an invisible 10 here, raised to the 2 equals that. Last time we checked, of course, x 10 to the square, that will be 100. And this is a square quadratic equation, so we equal it to 0. So x squared plus 15x minus 100 equals 0. Factors of negative 100, that gives me 15. That would be x plus 20, x minus 5. 20 times negative 5 is negative 100. 20 minus 5, positive 15. 0 product rule, x plus 20 equals 0. Therefore, x equals negative 20, or x minus 5 equals 0, x equals 5. Two solutions, however, we have to always verify. Of course, when x equals negative 20, I may not find the log base 10 of negative 20. So this one we eliminate. When x equals 5, we may find the log of 5, perfect. And 5 plus 15, that's 20. That's also safe. So one solution, x equals 5. Let's work on this one. Log base 10 of 2x minus log base 10 of x minus 3 equals 1. When we are in a difference, same base, we could use the quotient rule. Over here, of course, we use the quotient rule to condense, to collapse these two. So therefore, what do I have? Log of 2x over x minus 3 equals 1. In the previous example, how do we multiply? This was because of the product rule. Now we have base 10. So same old 10 raised to the 1 equals 2x over x minus 3. Notice that here we have fractions, so we will multiply by x minus 3 on the left, x minus 3 to the right, so we can simplify, eliminate the denominator. So I have that 2x equals 10x minus 30. Solving for x, we can add 2 to 30, subtract 2x. Just the easier will be to subtract 10x. 2 minus 10, that will be negative 8x equals negative 30. And we divide by negative 8. X equals positive 30 over 8 or 15 over 4. And we are done. Once off. Of course, when x equals 15 over 4, 15 over 4 is, this is number is 3 point something. Let's assume that it was 12 over 4, it will be 3. So if 15 over 4 is more than 3, 3 point something. 3 point something minus 0 will be positive. And here 2 times a positive number is positive. So we are safe. Let's try the following examples. Log base 6 of x plus 4 plus log base 6 of x plus 3 equals 1. Same base, we may multiply the arguments, things that due to the product rule. So we have log base 6 of. So here we are applying the product rule. So let's see what we have. X times x, that will be x squared. X times 3, that will be plus 3x. 4 times x plus 4x. 4 times 3 plus 12 equals 1. If we combine like terms, we have log base 6 of x squared plus what we have 7x plus 12 equals 1. Now we go to exponential. 6 raised to the 1 equals x squared plus 7x plus 12 equals, of course, 6 to the 1, which is obviously 6. When we solve quadratic equations, we equal it to 0. So x squared plus 7x 12 minus 6 plus 6 equals 0. Factors of 6, that gives me 7. We add them, 6 and 1. So x plus 6 times x plus 1 equals 0. When x plus 6 equals 0, of course, x equals negative 6, or when x plus 1 equals 0, x equals negative 1. So we have here x equals negative 6, or x equals negative 1. Oh, the two numbers are negative, so we log those online negative numbers. We should kill both numbers. Not quite. When x equals negative 6 plus 4 indeed is negative 2. So thanks, but no thanks. Now when x equals negative 1 plus 4, that's positive, so we're still safe. And when x equals negative 1 plus 3 is also positive. So even though the number is negative, when we plug it in, it respects the domain. So we are still safe. So one solution, x equals negative 1. Let's do example number 14. ln of x plus 1 minus ln of x equals 2, same base, in this case e. Difference, we subtract as per the quotient rule. We subtract, so we have ln, we have ln of equals to x plus 1 over x. Back to basics, e to the 2 equals x plus 1 over x. Base e raised to the 2 equals x plus 1 over x. We may multiply by x, both sides of the equation, so we can get rid of the denominator here, x over x bye-bye. So now we have e squared times x equals x plus 1. We want to have all the terms that are variable in one side of the equation, so we subtract 1x. So I have e squared times x minus 1x equals 1. Recall there is an invisible 1 here. So notice that, of course, now we can factor out the x. So I have x squared minus 1 equals 1. So for x, of course, we may divide by x squared minus 1. So this one would be x equals 1 over x squared minus 1. I do realize I'm out of the range of the camera, so give me just 1 second. So what do we have? X equals e squared, 1 over e squared minus 1. Notice this number e squared is 2.71 squared, so it's positive, minus y1 is positive, so the whole fraction is positive. When I add 2x, a positive number is positive, and attempting to find the ln of a positive number, we are safe. So we are okay with this one. Last example, log base 2 times log base 11 of equal log base 11 of. The 2 can be brought inside as the exponent. So what do I have? Log base 11 of x plus 2 squared equals log base 11 of 4x plus 7. The same base. That means that the arguments must be the same. So what can we conclude here? That x plus 2 squared, as per the equality rule, x plus 2 squared equals 4x plus 7. This is as per the equality rule. Okay, so now we are solving a quadratic equation. However, I need to expand this one so we can equal it to 0. So x plus 2 times x plus 2, that will be x squared plus 4x plus 4 equals 4x plus 7. We may subtract 4x, so x squared, 4x minus 4x 0, we may subtract the 7. I'm going to send it backwards. Let me do it for now. 4 minus 2 will be negative 3 equals 0. So now I have x squared minus 3 equals 0. Quadratic formula, well, this one is better to solve using the square root method. This is what I wanted, the 7 here. So I have x squared equals positive 3, the square root, x equals plus or minus radical 3. So now I have two solutions. Remember that the square root of a radical 3 is 1 point something. So anyway, so when I plug it back, 2 plus square root of 3, that's good. 4 times the square root of 3 plus 7, that's positive. What happens when it's the minus the radical? Remember the square root of 3, as I said, is 1 point something, it's less than 2. Of course, the square root of 4 is 2, so the square root of 3 has to be less than 2. When I have 2 minus radical 3, that's still positive. And when I have 4 times square root of 3 plus 7, that one better be positive as well. This one I cannot do mentally, so let me go ahead and try this one. So if I have the square root of 3, let me do that again. If I have 4 times the square root of 3, that would be negative. Again, so negative 4 times the square root of 3. Okay, negative 4 square root of 3. Let me close parentheses, and then I do what? Plus 7. Equals, it's a positive number. Good. Okay, so we'll accept both answers. Plus the square root of 3 and also the minus the square root of 3. So we have two answers. What are my two answers? Negative radical 3 and positive radical 3. Done. Thank you.